Welcome. My name is Nicholas Alaloglu, and today I'm presenting our work exploring the limits of deep image clustering using pre-trained models along with my collaborators from the University of Düsseldorf. Image clustering is an unsupervised task where we aim to assign a semantic label or group to each image given a predefined set of clusters or classes. Image clustering is a very challenging task because the class distribution is unknown. Second, because images need to be classified consistently, meaning that images of the same class should be grouped together, and confidently, meaning 100% prediction probability in a single class. That's why methods are typically prone to degenerative solution, where all samples tend to be assigned in the same single cluster. Existing state-of-the-art clustering methods employ a multi-stage approach, where in the first stage, contrastive learning is employed, while in the second stage, we use the learned network, the feature space of the learned network, to mine the k nearest neighbors to create pairs, possibly positive pairs that share the same label, while even though we know that these pairs are noisy, they try to account for the noisy pairs in the later stage. Our work is significantly different because we test and benchmark relevant representation from different types of supervision for 17 pre-trained models. And comparing with k-means, as you can see on the right, we're using TIMI, we provide an average gain of 6.1% in terms of clustering accuracy over k-means on ImageNet. Our self-distillation framework is called TMI and is based on the pointwise mutual information objective over a pair of mine nearest neighbors on the feature space of the backbone Z. On the top right, you can see that the denominator consists of the predictions Q of the student and teacher, abbreviate subscript as S and T respectively, where the numerator tries to align those predictions, while the denominator is simply an exponential moving average over the clusters of the mini-patches. Importantly, we introduce a hyperparameter beta that downscales the denominator and makes methods less prone to collapse or degenerative solutions. And in addition, we provide a theorem that shows that maximize the PMI objective with true positive pairs without beta leads to an optimal classifier under mild assumption. The final loss in our work is the symmetrized version of the PMI objective. Importantly, TIMI introduces an instance weighting term for the noisy nearest neighbors that is at the top right, as you can see, the inner product of the teacher predictions from the same head, while, and as you can see in the bottom, we aggregate the information from multiple heads in contrast to previous work by taking the mean, forming the final loss of TIMI. Experimental results on ImageNet show that without using ground truth labels or external data, and by simply using the self-supervised vision transformer along with TIMI, we obtain a 61.6% image clustering accuracy on ImageNet, which is the new state of the art that significantly outperforms previous methods on this task. We create another baseline by substituting our objective with a scan loss with the same hyperparameters in our self-distillation framework. And we also show a 2.8% improvement on clustering accuracy on ImageNet and significant improvements over k-means. Thank you so much. Feel free to